So now we're going to move to the most exciting part, which is actually talking about the scheduler. So in order for us to do that, let me pull up the Blackboard here, and then let's talk about how can one CPU, like a single CPU, run many programs. And of course, it can run many programs like sequentially, one after the other, but that's not what we want. What we want is it has a task T1, it has a task T2, it has a task T3. And what we want it to do is run this task for some time, then jump on to running this for some time, then jump on to running this for some time, and then jump on to this and kind of, continue from where it had left, move on. So then the way this should be imagined is we have got task 1, task 2, task 3. It kind of be extended to more than 3 tasks, but we'll just deal with 3 tasks. We'll talk about the prerequisites and what are the preconditions. Um, but the idea is this, that it starts off with, let's say, task 1, runs it for some time, pauses here, then jumps here, goes on to running it for some time, pauses here, goes here, runs this for some time, pauses here, and next time around it comes back to executing the task T1 again. It picks up from where it left off, then runs this for some time again, and then pauses and goes back and continues task T2, and so on and so forth. And it kind of keeps on doing this until the tasks exit. Or you can imagine that this can be a while one loop, this can be a while one loop, and this can be a while one loop, right? So it kind of never returns. You can imagine that T1, T2, T3, the tasks or the functions, they never exit. They just have like a while one in them and they go on doing something in repeat forever. Let's start there. And the reason we are wanting to take a case of tasks that don't terminate is because we want to free ourselves of the burden of adding a task and removing a task on the fly. Let's not focus on that problem. Um, Once we can figure out how to run 3 tasks in kind of parallel, parallel in the sense that the CPU is doing a round robin, so to speak, and it's doing round robin so fast as perceived by the as perceived by the humans, that it almost feels like 3 things are happening in parallel, right? You could kind of blink an LED, let's say red LED here, blue here, and green here, and it almost feels as though the 3 LEDs are getting kind of, are blinking simultaneously. But let's say the rate and all of that is controlled by each of the tasks. Well, long story short, hopefully you caught on to the idea that there are 3 tasks that never end. They do some computation, and what we want to do is kind of execute them in parallel, get a single CPU to execute them in parallel. Now again, when we say one CPU executing tasks in parallel, it's really not parallel, it's kind of sequential, but it's sequential in the sense that it kind of does little bit of execution for each of the tasks and does it so fast in terms of round robining, or in terms of a scheduling mechanism called round robin, that we almost perceive it to be happening in parallel, right? So that is the idea. Now the question is, how do we go about getting our CPU to doing this? So first thing first, recall that wherever the program counter is pointing, that is essentially, uh, you know, the location from where the CPU is going to fetch the instructions. Okay, so which then means that if we can somehow change the program counter value at exactly this point, in T1 to the starting location of T2, then there is a chance that the CPU will kind of execute T2. In fact, it will start to execute T2. Similarly, when this point, let me call this point A, let me call this point B, and let me call this point C. So when it hits the point B, if we can somehow get the CPU to jump, or rather the program counter value be set to T3, the starting location of T3, then the instructions will be fetched that correspond to T3. And exactly at the C point, then, if we could set the program counter back to the location A, or A plus 4, because A is where it paused, let's say. Um, so the next instruction is what it wanted. So anyways, the idea being, if the program counter can be restored to this value, then it can continue to execute T1. So the important information here is PC is involved, and then we are saying, some trick to changing PC that is involved. And the third thing, which I'll write down here, third thing is, when from T3, when we were wanting to return to T1, we wanted to essentially go back to the location A, or A plus 4. So then the idea is, somehow we should be saving information about where we paused. So that is the third thing, right? Program counter needs to change. There is a trick involved in doing that we'll explore. But then we also have to remember where the program counter was for the previous task. And not only that, let me now get rid of all of this. Not only that, recall that our CPU, as per the programmer's model, has a lot of registers in it, right? Status registers, program counter, other some interrupt related registers. And now when it is executing T1, the registers are holding values as corresponding to the computation of T1. So when we change the program counter to T2, somehow the partial state for T1 is still in the CPU, right? Only PC was changed. And then after executing T3, when we return back here, well, the CPU has stuff that corresponds to T3, because T3 task would have corrupted these registers. So that then also means that somehow, not only do we have to remember the program counter that the CPU was pointing to when we wanted it to shift to T2, but it should also kind of retain the partial calculations that T1 that were done as part of the task T1, which means the CPU registers need to be stored to, saved rather, right? So then what are the things that we need to do? The PC needs to be changed, right? The trick to changing the PC, so there is some trick to it that will come to. The third one is save PC before switch, and then we are going to modify this point to save CPU registers before switch, right? So we have got T1, T2, T3, and what we do is let T1 run for some time. Then at this point A, we should save PC plus CPU registers, save all of these, and where, that's a question mark, we'll come to that. But not only save these, also set the program counter somehow to T2, right? And as it comes to B, save, PC plus reg, all the CPU registers to some place and then switch to T3. And as we come back and we do the same thing here, so, PC plus reg, we have to save those. And when we come back here, we actually restore these registers. So the CPU kind of is tricked into executing program right from the value, let's say right from the memory location A. Right? So that's somewhere the trick, no, not the trick, but that somewhere is our intention. If we could do something like this, turns out we will have 3 programs executing in a round robin fashion. Again, if things are not clear so far, rest assured, we'll dive into the details of how all of this happens. But if you're not convinced about these 3, I would request you to kind of go through this lecture once again, because this idea of being able to save CPU registers and restore them is very fundamental to how tasks are scheduled, and every scheduler uses this trick. It's about getting the CPU to save its current set of registers and kind of uh, adopt new values for those registers, specifically the program counter that points to the location where new instructions for the next process needs to be fetched from. So yeah, if you're not convinced with this, do give this lecture another try. Watch this in loop until you're convinced. If not, leave us questions and we'll attend to those as well. With this, I'll see you in the next one.